Thank you. So what I'm going to talk about today is I'm going to share the screen so you can actually see what I'm seeing. And where is it? Lost everything again. It's a part of the course. And now I need to make this go away. Sorry. As part of this course, I'm teaching during the winter term at Charles University in here. You can see it has a lot of different topics, starting with introductions to data science, some ideas about what data science is, and going through the data structures into complicated stuff like interpolation, regression, and application of spatial dimensions in machine learning. I have taken a small part of it, and I have created a notebook which lives currently on a GitHub repository. So I want to ask a question. Is there anyone in the room who would like to run the stuff on their own laptops as I go through this? If so, I will explain how to do that. If not, I can. I suppose it's a no. I don't hear anything, so.
It's a microphone. Martin, can you hear us now?
Yes, yes.
Okay, there's one person that would like to run through at the same time, but he said only if it's not going to cause any trouble or extend it too long.
No, it should not. It should not. So for that person, try going to this repository. It's github.com martinflies Saarbrücken-workshop. And in there, you will see that there's a notebook and there's also some Pixie files in here, which is the way how you can reproduce the environment. So ideally, what you would do is that you would go to code, you download the repository, or you can clone it with Git if you are familiar with Git. But if you download it, then you should be able to use Pixie to automatically create the environment which can run everything in that notebook. So that requires two steps. One is to install Pixie, and there's a link with instructions how to do that. It's fairly simple. And then you will just use this command, pixie run JupyterLab, which will start the interface, which looks like this. And you will be ready to go. You will need to run this from the folder where you have downloaded all this. If you need assistance on site, ask Lisa. Lisa will wave right now, so she will help you with terminal and stuff if you need some. I called this a brief introduction to spatial data science, and I was kind of thinking what exactly it should cover. And I opted for three different components coming from three different lessons from the original course. So I will explain a bit more on spatial weights and relationship between individual polygons, individual geometries, and how we treat those and how we define those. Then I will talk about spatial autocorrelation, and we will finish hopefully with spatial clustering. Given you are all in a room and I'm kind of on the screen, it's kind of complicated for me to see where you have a question. I also see on the camera only 4 people in first 3 rows. So I will try to stop frequently to give you a space to ask for questions. But also feel free to interrupt me, to just grab a microphone and interrupt me, and I'm happy to answer anything as we go. Yeah, so we will be working primarily within the context of Bicel, which is the, let's say, family of packages for spatial analytics. So Bicel stands for Python Spatial Analytics Library. And it can do all sorts of things, from fundamental representation of data structures required for spatial statistics to some advanced predictions and autocorrelation analytics and stuff like that. So when I say spatial weights, what I actually mean by this, assume you have a set of geometries representing countries in Europe, for example. If I have them in a table, where in a data frame where I do have a geometry allocated assigned to each of those, I need to find a way how to mathematically encode which country is neighboring with which. So let's say that I want to know that Czechia has 4 neighbors, and those neighbors are Germany, Austria, Slovakia, and Poland. For that, we are using a data structure called spatial weights. And in principle, it's a matrix where you have all the states along x and all the states along y axis of the matrix. And whenever they meet, you have a weight representing the spatial relationship. In terms of the relation I'm just describing, whether I do want to capture the neighbors only, I will either have a 0, which means that on the row for Austria and column for Belgium, I will have a 0 because these two are not neighbors. But on the row for Austria and column for Slovakia, I will have 1 because those two are neighbors. So in principle, we are working with this kind of representation so we can take the spatial dimension represented as geometries and turn it into a form which can be easily processed through statistics. But let's do that visually. I'm importing a bunch of libraries in here. Important ones for us are GeoPandas, which is the library that is handling the spatial data in Python. I hope it's large enough. I can zoom in if you need to let me know if that's not visible enough. We will be working with the graph module of the libpycel, which is the one dealing with the spatial weights. We will be looking into ESDA package, which stands for Exploratory Spatial Data Analysis, and we will use this to do autocorrelation. And then we will be doing some stuff with the cluster module of scikit-learn when we will do some spatial clustering. We will be working with 3 different data sets. And the first one is a data set of basic settlement units, which is like a statistical boundary for Prague. And we have, I don't know how many, not a ton of polygons which look roughly like this. So you can see that we have a continuous area of polygons, no gaps, no overlaps, nothing of that sort. But even though we see visually that these two are neighboring, we have no mathematical representation of that as of now. Which means that we need to build spatial weights. We need to define which geometries do we consider within a neighborhood of which, and we have many ways of doing so. And the way you choose should reflect the expected spatial effect of neighboring polygons or points or other geometries within the context of whatever we're trying to predict, model, understand. The most basic, most common way of representing relationship between multiple geometries is contiguity. If we have polygons like we have up here, we can easily try to say, okay, this polygon is a neighbor of this one because they share a portion of their boundary or they share a point on their boundary. The first contiguity we will create here is so-called queen contiguity, which means that two geometries are considered neighbors if they share at least a single point on their boundaries. We are using the graph module from libpysal and we are creating the graph class. You can see that this is indeed a graph, and we are using the build contiguity method, giving it a data frame and specifying that we want the queen contiguity, not the root contiguity. I will explain soon enough what the root contiguity is as well. And in the end, we have a graph with 953 nodes. Those are 953 geometries we have, and more than 5,500 connections between those. If I look, for example, for a single location on Alberto, which is where the university campus of my home university is, we see that it has roughly 10-ish neighbors. And we see their names. We see the index that has been used in here. So if I will show you how this Prague data frame actually look like, what I should have done, you'll see that it's indexed using the name of each of these basic settlement units, and those names are then used within the graph to map one to the other. You can see that the values of the weight are always 1 in this case, because we are saying, is it neighbor or not? There's nothing else. If I want to just extract the value from there, I can just index it with the name of the
Martin?
neighbor. Yes, go ahead.
Could we go a little bit slower just because it's a bit fast? Or I think
We can try that.
Hi, it's really good, but for me, from the acoustical situation in the room, it's a little bit like 5% or 10% too fast for me to grab the language you are speaking.
Okay. Yeah, I will try to slow down. I'm kind
Thank you.
of rushing a bit as I'm mindful of the time, and I want to show you something interesting. And I also hope that I'm not kind of skipping too much of stuff. I assume at the moment that there is some basic understanding of how Python works in the room, because I cannot simply just start from the very scratch with that. You would have to have much more time than we do. But in principle, what we have done here is that we took the data frame, which is stable with our polygons, and we built a data structure which encodes their spatial relationship based on a rule of queen contiguity, which means that we consider two geometries a neighbor if they share a single point. A very useful way of looking at this kind of data structure is actually plotting it. So if we do that, we'll see that the black lines are encoding the internal structure of the graph, are encoding which polygons are neighbors of which other polygons. We can visually explore this. Just note that it's always kind of linked to centroid of the geometry, which in case of some very strange shapes may mean that it's actually not inside. I believe it's using centroid.
As
So
the
this is this-
feedback now, I understand quite well. Thank you.
Great,
Thank you.
great. So this is the Queen contiguity visualized on a map. And try to remember how this map looks like, because as we will go through, we will be comparing it to other ways of defining weights, and we will see that it can change quite a bit depending on the rules we apply for neighborhood relations, essentially. You can also do this statically if you want, as a static map rather than the interactive one, but I will let you to kind of explore this in your own time. The graph object has a lot of interesting properties. We can, for example, ask about the cardinalities, which is an attribute that holds the information about number of neighbors of each polygon. So if I will look for cardinalities for that one basic settlement unit where the university is, I see that I have 9 neighbors. When I was looking at it before, I was close with 10, but not necessarily. And this is a simple pandas series, nothing complicated. If you know a basic Python for data science, you have probably seen pandas before. So this is a simple pandas series, which just holds the number of neighbors each of the geometries has. Because it's a pandas series, we can easily ask what is the mean number of neighbors, which in this case is nearly 6. And the maximum number of neighbors is 15 for, we can ask for which, why is it? Never mind. It's 15 neighbors, so going from, I believe, 1 to 15 would mean 6. We can plot the distribution of number of neighbors, see how it kind of behaves, if we would like to do this kind of exploration. We can ask how many geometries are encoded within the graph, which is 953, which if you check with the Prague data frame, we will see that it exactly matches the number of rows. If we have something which is not entirely contiguous, we can have islands, we can have some erroneous geometries which are not properly linked to properly snapped to the neighbors. We may have some isolates, which are observations with no neighbors. But in this case, you can see that this is an empty list, so there are no isolates. And we can ask for a summary of the graph, which gives us number of nodes, number of edges, connected components, isolates, and some other useful types of information, some of which, like those sums of weights and traces, are useful within subsequent statistics, and you don't necessarily have to look into those yourself. So I've created a visual exploration of the whole graph, but we can also use the information from the graph to create smaller subsets like this. So this is the Albertov, the one basic settlement unit we're looking at. The faculty where I usually sit is just here. And we have created a map which showcases our polygon, which showcases the neighbors, and which showcases also a portion of the graph. And again, I will probably let you explore a bit on your own how exactly this has happened. There's a lot of documentation within the notebook, so you should be able to get back to that if you would like to understand more. Another type of contiguity which is commonly used is so-called rook contiguity. It's very similar to queen contiguity, but it is more restrictive. And it considers two polygons neighbors if they share at least one segment on their boundaries. So one point is not enough. It has to be a segment. And you can think of a chessboard where queen contiguity represents where queen can move on a chessboard, while rook contiguity represents where rook can move. And you can potentially also do the bishop contiguity if you want to do so. So we have the same number of nodes. We have 5,210 edges if we use rook contiguity compared to 5,670. So we have lost certainly some relations. And the decision on which of these you should use is usually depending on your assumptions about the effect of one polygon to the other. There's no rule of thumb, essentially, of what you should do. In a real world, you will see that the difference between queen and rook is minimal. Like in here, it's about what 10% of edges. So it may not play a huge role, but in some cases you may just say, if I don't have a shared edge, therefore a flow of certain observation cannot move from one to the other. I don't want those two to be neighbors, but in other cases you just want to, so it's all up to you. We can also derive bishop contiguity, which is contiguity which is a result of a difference between queen and rook. So it's only the polygons which share only one vertex but do not share the edge. So we can have a look at the difference between the queen and rook also visually. If I just subtract the rook contiguity from the queen contiguity, so you see we have 460 edges which are in one but not in the other. And visually that looks like this. So we can also have a look at how that looks like. So I'm using the static map right now. We could also do the interactive above. That's a way how to define neighborhood relations based on contiguity. Is there any question to this session, to this section? Is a movement.
Not so far, Martin. You can go.
Okay. The other way of defining spatial relations is by a distance. So we're not necessarily interested by the shared boundaries, or we don't have shared boundaries because we are dealing with points, for example. And we want to say that everything within a certain distance-based rule is a neighbor. That distance-based rule can be k and n, so k nearest neighbors. And I can have a assumption that roughly 5 nearest neighbors play a role within the phenomena I'm studying. Because distance is much faster when done on points. Graph assumes that we are passing points. So we can generate centroid representation of our geometries and set it as active geometry. And then we can create a graph using the build k and n method with 5 nearest neighbors. So we have less edges than before, but not by much. if I do 6 nearest neighbors, we will have roughly the same number, because you can remember probably that the mean value was 6 before, but let's stick to 5. And if you make visualization out of that, you will see that this is slightly different than before. But nonetheless, valid way of capturing the relation between different geometries. If you don't have the geometries, you can also create this from array of points, but that's probably not necessarily important right now. So this is defining, this is using distance to measure the distance to 5 nearest points and assume that or essentially to measure distance to all nearest points and take out the 5 which are the closest. But we can also use something called the distance band when we say, I want to consider a neighbor everything that is within 1,000 meters, 1 kilometer around. Then I can use the distance band builder on the graph. I'm again passing the data frame with centroids right now, and I'm specifying the bandwidth of 1,000 meters. And we have a bit more edges, but again, not a huge amount of above the original number of edges, which was 5,700. The Albertov settlement unit has more neighbors than it had before. And if we visualize this, this is very different than before. We can see that in the city center, which is in the middle of the map in here, the graph is very, very dense. While on the peripheries, we also see some disconnected components, which is something we haven't seen before. And that's before, within 1 kilometer of these, of the centers of these settlement units, there's only one, or maybe not even one. So we can briefly check, do the summary. We can see that we do have 30 connected components. A connected component is...
Hello,
Yes?
Martin. So we have a question here
Go on.
about, so when you specify the number of nearest neighbors, k equals 5, and then, yeah, underneath the graph, you then say, yeah, how you need to note how you need to specify the number of nearest neighbors you want to consider with the argument k. And we were wondering what the box does below this PTS and graph build k and n, what you're doing there.
I have skipped this one. This is just to give you an indication that the builder for build KNN can work with both data frames. So with Prague, which has right now the point geometry, but it can also work with an input like this, where I have all the coordinates.
Yeah, clear, Martin. Thank you.
Yeah, occasionally you just load a CSV with X and Y's, latitude, longitude, whatever. And you don't necessarily have to create geometry out of that if you don't need it for anything else. So you can just build the KNN directly from the coordinates. That's why I've skipped this, because it just, yes, you can do this, but it's kind of not necessarily important for what we're doing here.
Okay. And also a question from my side. So you usually in like also examples that I've been following in your work, you're using k nearest neighbors. So why is distance band? Why do you use this less, or what might be the applications of using distance band in morphometric analysis?
This very much depends on the assumption of the behavior of the phenomena you are attaching to all these geometries. So if we are, for example, trying to model noise, what's important for you is how far point generating noise can be heard from, right? So in that case, I'm interested, okay, I know that I have a siren, and this siren can be heard from 600 meters away. So I want to make a distance band within the modeling pipeline that captures these 600 meters. But in other cases, you know that the phenomenon you are modeling is behaving more topologically, let's say. And that the actual distance doesn't matter as much as the fact that after three nearest neighbors, the fourth one makes a little effect. So the applications are different. Very often you want to use k nearest neighbors if you have very uneven distribution of your geometries. So what happened with the distance band down here is that in the peripheries, the graph is extremely disconnected. This would break some statistical models, as there would be not enough information to work with on those, and everything you would model on these peripheries would be statistically insignificant. So that's where KNN is useful. What happens sometimes is that you say, I want to consider everything within 500 meters and or let's say 5 nearest neighbors at the same time. So if those 5 nearest neighbors are further away than 500 meters of the distance band, you just add them on top of that. It's kind of reconnecting the disconnected components to the main graph to ensure that the certain statistical operations are actually solvable. It very much depends on what you are trying to model. The work I've been talking about yesterday, we are usually trying to work with topological distance. So it's even more complicated. We are using contiguity, but we are treating neighbors not only if they share a point, but if you can kind of walk through. So it's a neighbor of neighbor, a neighbor of neighbor of neighbor, up to 3, 5 topological steps. So that's a different K. There's a huge variety of ways of defining the weights, and there's not a rule of what should be used when. It's very much domain specific, and you need to understand the behavior of the phenomena you're trying to model in order to correctly pick the weights. And in some cases, you are just doing the same analysis with multiple options to compare them to see how it behaves, to understand what should be the right choice and what are the implications of one or the other, or in which cases the results agree between different definitions of weights, and in which cases they do not agree, so you can make your conclusions in a more reliable way. Does that answer the question a bit?
Yeah, that makes sense. Thank you.
Great. Another way of generating weights is something called block weights. And that's useful, for example, when you know that your geometries are kind of grouped in regions of the hierarchy. and that the phenomena you are modeling, for example, budget allocation, is influenced by any other within your region, but not anything else. That's called block weights and block contiguity. And in our data set, we do have the cadastral area. So you can see that this is higher order. So we have multiple geometries falling within each of these. So we can use this column, this categorical column, capturing cadastral region. I don't know how it's called properly. As an information to build the block weights. We have way more edges than we had before. The Alberto one doesn't have that much more, but if you plot this, you will see what actually happened. You can see how the graph generated all these enclosed connected components where everything is connected to everything inside, but is disconnected completely from anything around. So in this case, if I will do the summary, I will ask about the number of connected components. For example, we have 112 connected components, as each of the cadastral regions is a component on its own. We even have two isolates in this case, because apparently in some cases, the cadastral region matches the extent of a single settlement unit. So those are ways of few of many ways of defining neighbors. And if we pick one, let's say queen contiguity, let's say KNN, let's say distance band, we can then ask about the spatial configuration of the variable you're interested in. And a graph can directly do some basic description for you. So let's say that we are interested in the spatial distribution of area of each settlement unit. So I will set the active geometry back to my original polygons, which is in the geometry column. And I will assign area, logged area or as a column. I'm using log because the areas tend to be distributed quite heavy-tailed, and using log of area actually resolves this issue for us. And then I can use the graph derived based on queen contiguity to describe the distribution of the area around each of our polygons based on their neighbors. So I had a number, that's fine. So what is happening here is that for each of the geometries, I now know what is the mean value of our logged area, what is the median, minimum, maximum, and standard deviation. If I join this summary, this description back to our original data frame, you can assign it as additional columns, and then we can plot those columns on maps. So while this is the original area we have measured directly, this is the mean of the area within each neighborhood defined by queen contiguity. This will be standard deviation, and this would be the maximum. So this already shows that while this is kind of messy and it's hard to distinguish what happens in here, if we look at the mean values, we will start seeing some patterns in here, seeing that probably these are more densely populated areas in the city because they tend to be smaller than these on the peripheries. So describe can give you a range of statistical measures for your variables, but it doesn't consider the actual value of the weight. Because so far, everything we've been doing was just encoding whether two geometries are neighbors or they are not. So it was 1 or 0. In other cases, you can even treat the value, let's say, as distant. So if we do k nearest neighbors, we can encode distance within the graph, and we can say, I want to make sure that whatever is closer makes higher effect than whatever they're further away. And then you can use this information in something called spatial lag, which works similarly to describe, but it essentially takes the weight of every single observation in your neighborhood and multiplies the weight with the value that geometry has and combines it all together. So with our queen, which has the Boolean weights where everything is 1, the queen.leg would give us a sum of areas. I could also normalize these. So instead of having weights which look like this, we can normalize or transform the graph into row standardized graph. Row, in that case, we'll see that the value has actually changed on the transformed one. So it's no longer 1 on each of those, but it's 0.011111 because we have transformed it in a way that the sum of all weights within the neighborhood is 1. So they are all equal. But if I do the same leg using the transformed weights, I will have to get different values, and these values are mean, while these with ones are sum. And then obviously if you have the weight different for every single of the neighbors because they are more or less important, because they are further away or they share more or less boundary, the lag value is affected by that. And you can also do something which is called a categorical lag. So if you have a categorical variable, categorical lag is trying to return the most common category within your neighborhood. If you have a tie, like there are 2 of Kie and 2 of Smichov, you don't know which one is that. There are some ways of resolving the ties, either by adding the value on the observation itself or some randomization of the result. That's introduction into spatial weights and the graph object which encodes spatial weights within Python. I will stop for a second, giving you space to ask questions before we will move on to spatial autocorrelation, which will use weights, but it will ask more interesting questions than what is a neighbor of what. Are there any questions?
I don't personally have any questions. Do any of you? No, I think we're good to move on.
Good, let's move on. We have 33 minutes and a lot of stuff. So you can see that there's a lot of description, lot of explanation, which I will happily ignore. And I'm going to read the different data set. This time one with different municipalities of Czechia and the results of the latest presidential elections in the country, the second round. You can see on the map the percentage of votes the winner, Petr Pavel, received in the second round. And because we are trying to look into spatial autocorrelation, our main questions here are there any spatial clusters where he either got more than elsewhere or less than elsewhere? And if they are these, where exactly are they? From the map, we can kind of see it, right? You can see that around Prague, there are some higher values. Up here, there's some higher values, while in these regions, we see some blues, so some lower values. But it's not enough to just eyeball it, to look at the map and say, yeah, these are large clusters of highs, clusters of low. We're scientists in the end, so we're trying to use science to statistics to help us getting to the answer. And we will use spatial weights again and analysis of a spatial autocorrelation to get to the answer. So I will build the green contiguity graph again. And I will transfer, I probably don't need to, yeah, I need to transform. I will transform it into the row-wise weights. So for this settlement called Razany, which is where my grandma lives, we see that we have 5 neighbors with 1s. After transformations, we have the same 5 neighbors with 0.2. Wait, and the reason I'm doing the transformation in here manually, because I want to do something called Moran's plot. Moran's plot is a very simple scatter plot. I hope it's somewhere here. Yeah, it's a very simple scatter plot where we plot the actual value observed on a geometry on x-axis and the mean, the spatial lag of the from the neighborhood on y-axis, and then we're trying to look for a correlation on the scatter plot. So let's save the lag of the percentage of votes for the winner as a column. So right now we have the original recorded result and the lag on a neighborhood. And we can skip this. And then let's do the same thing, but on a standardized values. So instead of going with the raw percentage, let's standardize this. So let's standardize the results and let's generate a lag out of standardized values. So right now we do have a couple more columns with the result for Petr Pavel in standardized way and the lag generated out of the standardized way, because we want to ensure that the Moran's plot, which I will show in a second, is nicely scaled and it's organized. It's oriented around 0. So as I said before, Moran's plot is just a simple scatter plot. It looks like this on the x-axis, we have the values tied to individual geometries, standardized values tied to individual geometries. And on the y-axis, we have the lag, the spatial lag for the geometry, which means that that's an average of neighboring municipalities in our case. And we can see that there seems to be some correlation. The slope we see here is a result of a regression, and that slope actually represents the strength of the autocorrelation. And this is a first indication that there is indeed some autocorrelation, but it doesn't tell us where it is. And it barely tells us how strong it is. The 4 quadrants, which are marked in here, are showing the geometries where we have high value observed on a geometry and high values also observed on the neighbors. On this quadrant, we see the opposite. We see, okay, there were low values observed, and all neighbors also had low values. But we also have quadrants where we have high values observed on the geometry, but it's surrounded by other municipalities with low value, or the other way. We have very low value on a single municipality, but their neighbors have, on average, much higher result. And we can use this type of information to compute Moran's I, which is a statistical assessment of the Moran's plot, which gives us the actual value we can use. We can compare with other observations, and we see that the Moran's I in here is 0.538, which is quite high for Moran's I. It can take values from 0, which means complete randomness, to 1, which means that there's I believe, I don't even know how it would look like. I don't think it's possible. But what essentially means that there are only spatial clusters of values. Because Moran's I is based on simulation of a random process and comparison of that with our observation, we can also check the statistical significance through the simulated p-value, which in this case is 0.01. So we can consider this value for Moran's I statistically significant, which means that we can conclude at the moment that there is indeed spatial autocorrelation in the data, and there are clusters of the, let's say, voter preferences. But we still don't know where they are. For that, we will use a local spatial autocorrelation. Before I will start explaining local spatial autocorrelation, are there any questions to Moran's plot or Moran's I? Okay. So local spatial autocorrelation is an extension of the global one. And it's trying to look at those 4 quadrants we've seen in the Moran's plot. And it's trying to put them on a map and trying to understand in which cases we can statistically significantly say that this is a cluster, and in which cases we cannot do so. The implementation is very similar to the global Moran's I. We use the ESDA package, we use the Moran local class, We pass in the value we are interested in. We pass in the weights graph, and we can get directly out of that the labels for different clusters using the critical value for statistical significance of our choice. We will use the most common 0.05. And we'll see that, for example, this specific municipality is within the high cluster, while these 4 in here are insignificant. But what does it mean spatially? It means this. What we have identified in here are clusters of high support for the winner compared to the overall distribution across the whole country. So around Prague, around other large cities, and also in the regions on the boundaries in here and here. And the reason for that is that the elections happened during the, I believe, first week of February, and that's where the ski resorts are. So people from Prague were voting in the ski resorts with their voting passes, while the generally more peripheral locations of the country were voting for the opponent of the current president. Again, we can play a bit with the critical value in here. We can try to be a bit more restrictive. Let's say I want the clusters which are only 0.01 critical using the p-value, so we see that there's a bit less of the information. Or we can kind of give it a bit more freedom and say, yeah, I will just 0.1. And that will probably struggle within the peer review, but you may want to have a look at that, or you may want to compare those and see where the clusters kind of tend to disappear if you change the p-value. Again, we can do this as an interactive map, as a static map, depending on your preferences. Obviously, for exploration, like we are doing right now, the interactive is great. For a paper, you probably want a static map, so you can use the cluster labels you've assigned here and just use those to generate a map. There are also other options how to measure both global and local autocorrelation, be it GRISC, Gettys ordered G, and other types of statistics. Most of those are implemented in ESDA, and their API is very similar. Moran's I is by far the most commonly used, because also it's quite straightforward when it comes to the understanding of how the algorithm works, for which we don't really have time today. In some cases, when you are dealing with categorical data or you are dealing with Boolean variables, you will need to use different ways of assessing local autocorrelation or generally spatial autocorrelation, but there are ways of doing so, and you will, without an issue, find some. And you can probably start thinking about, oh, but how would this type of analysis be affected by different type of weights, which is the precise question I would like you to ask and possibly try if you are trying to run this or will try to run this at some point. Because in here we have used Queen contiguity, but if we did, for example, KNN or distance band, the clusters would probably look slightly differently because the spatial lag, the average on the neighborhood, would be computed slightly differently. So always think twice about what makes the neighborhood, essentially, how we define this. And we got 15 minutes left, which I would like to use for a bit of clustering. But if there are any questions for autocorrelation, please go ahead and I will try to answer those.
We're fine. Please keep going.
Great. So clustering and regionalization. For this, we will use yet another dataset. And here we do have values of Scottish Index of Multiple Deprivation in Glasgow. And we will try to, I should probably plot it. I do have a plot somewhere. Here we go. So the geometries which look like this, and we do have information about subranks, about specific portions of the index of multiple deprivation based on income, employment, health, education, and so on, crime, and so on. And we will try to figure out whether there are some clusters based on these subranks within the city of Glasgow. If we compare those subranks and look for their correlations, you will see that, yeah, indeed, there are some correlations. For example, income seems to be heavily correlated with employment, quite a lot of correlation with health, but not so much with crime and so on. We can kind of go through this to understand a bit what our data look like and how can we expect this to unfold. I will be using simple k-means clustering, which means that I'm trying to distribute all my observations into a set of clusters based on their similarity using the values from all these subranks. It's k-means because I need to specify a number of clusters. This is the k. And there are a variety of ways of how to figure out which k is the best. But what I'm trying to do in here is to show you how we can plug a spatial information into something like k-means, which by default has no understanding of space. So if we create a k-means clustering based on our subranks directly, just simply using the k-means class from scikit-learn cluster module, we will get labels out of that. Each label represents one geometry and its allocation within a cluster. I can directly assign this as a column and I can visually explore the outcome. And these are all clusters. So it's decent for sure. What I can tell right now, because I've lived in Glasgow for 4 years, is that the city center and the west end of Glasgow, together with the southern parts in here, are kind of the more affluent parts of the city, and the rest is less so, let's say. But from the spatial data science perspective, there was no spatial data science. There was no spatial component in it. The fact that it's linked to geometries is just a consequence. And I would like to use the information about space and the whole process to make it a bit better. I will skip this and to be mindful of time. What we'll do is that we will again build contiguity. This is root contiguity. But in contiguity, we will transform it and we will create a leg of each of the subranks as another column. So right now, we have not only the original columns, but right now we have additional new columns which capture the average rank around each of the, I believe, output areas. I think there was a sense output areas. And what we can do right now is that we can take these columns and use them in the clustering algorithm alongside the original ones. So we will get a list of these columns and combine it with the original ones. And these are the columns we will then use within the new k-means clustering. Again, the same number of clusters, just using the original observation and the like together. And the result of this is a bit more spatially organized. There's a less spatial noise if we compare it to this. You can see that the regions are way more kind of consistent in here, but it's still not as great as we might want to see it in some cases. You could obviously include only the length variables. In some cases, it makes sense. In other cases, it's not so great idea. But you can also use completely different type of algorithm. And that's regionalization. Regionalization or spatially constrained clustering is a family of algorithms which tend to subdivide the spatially defined set of observations into regions in a way that the characteristics of each region is as distinct from any other region as it can be. We will use the same module from scikit-learn, but we will use agglomerative clustering. And again, we have to specify a number of clusters. So let's stick to 5. But we can define a connectivity, which is our graph in a form of a sparse matrix or sparse array in this case. It's not necessarily important to explain why we are passing this sparse. Just that the agglomerative clustering understands any sparse representation of connectivity metrics or contiguity metrics, and we can get one out of the libisal graph object by calling .sparse on it. And we can ignore the spatial like right now because we have the spatial dimension embedded in the algorithm itself. And if we get the labels out of this and plot those, you can see that the result is completely different, completely something else than it was before. You also may notice that the blue cluster is kind of divided, so it's not a single region. The reason for that is that there are 2 connected components, and the scikit-learn is automatically completing it to ensure that the algorithm can actually result in something. And the reason we have 2 connected components is that there's a river Clyde going in the middle of the city, which is disconnecting the south of the city from the north of the city. That's one nice reason why you may want to use something like k-means, k-nearest neighbor, or distance band instead of contiguity, because in this case, these 2, even though they are right across the river from each other and connected by 2 bridges, they are seen as completely separate entities, and there's no neighborhood relationship between those. But as you can see, the result of this clustering are 5 clusters which are completely spatially distinct, which is what you would expect from regionalization. And then you can just simply use GeoPandas method called dissolve, and you can dissolve the original geometries by these new labels to get nice geometries representing the boundaries of individual clusters. And this is in principle how some of the work I've been showing yesterday is being done. So we take the values, we measure stuff on individual buildings and streets and so on and so on. And then we are trying to find spatial clusters in those and then dissolve the boundaries to get something like spatial signatures with which we can then work further and ask, for example, for hierarchy of settlements or internal structure of different places around the country. And that's the end. Yes.
Oh, okay. That was the end.
Yeah,
but
that's the end of
before
the
you
book.
wrap up, I wanted to ask you two questions. One is, you know, where you were showing the bridges in the river that separates it completely. Is there any way to use those bridges to build contiguities between the north and the south regions or areas of the river, so that they are connected somehow and it can perceive it as connected?
You need additional information to do so. So I see the bridges in here because it's a base map underneath.
Sure.
Yes, yes, generally yes. You can also, what you can also do is that you can create the spatial weights based on accessibility on the street network. So rather than using just the geometries, you will use the geometries and the street network that goes through the city. And you say that I want to consider a neighbor everything which is within 15-minute driving.
Right.
In that case, the issue with bridges would disappear.
Okay, so I was hoping there would be a straightforward, easy way to do this additional contiguity.
Well, the one thing you could do is to do something called fuzzy contiguity, which essentially buffers the geometries. So if we know that the widest part of the River Clyde is something like 150 meters, you can build a fuzzy contiguity with something like 80 meters buffer, which means that in that case, it would buffer the southern part a bit to the River Clyde, the northern part also a bit to the River Clyde, at which point they would meet.
Excellent. Okay, that sounds like an
And
easier solution.
yeah, or you can also use Voronoi-based Voronoi-based weights, again, which would automatically infill these areas in between.
Okay, the
So
second
there are
question
ways.
yes, thank you. The second question I have is I'm not clear why number 5, or was it the blue one, was split in two parts.
Yeah.
Given that there are these contiguity constraints, how did it manage to bridge the northern and the southern part?
The reason for this is this warning, which is we show in here. The agglomerative clustering algorithm is unsolvable if you have multiple disconnected components. So what scikit-learn is doing for us is that it automatically creates a connection between the two. But we have no control over where the connection happens. So what actually is happening here is that most likely something like this is treated as a neighbor of this, even though it's not a neighbor in practice. We would have to treat this ourselves in some way, or we would have to do the regionalization of the south and the north independently if we want to ensure that that we don't have to figure out how to connect the two components. So it's just random. I'm not sure exactly how it works, but I think it just picks one from the one component and one from the other component and assumes, okay, I'm putting a connection here, and warning you, hey, there's a connection here. And this is the consequence of that additional connection, which is there just for the purpose of solving the algorithm at all. Otherwise, it would just error out and you wouldn't get anything.
But in any case, the underlying variables are the ones you showed us earlier for the k-means.
Yes,
So
yeah,
maybe if you had asked for 6 rather than for 5, then these two would be possibly, maybe, who knows, whatever, separate.
You can check that.
We can try that.
You can easily check that. It did not
No.
happen.
Okay.
But what you would want to do essentially in here is that you would want to ensure that the disconnected components do not exist in the data and that you make the connections in a sensible way, like through the bridges, rather than letting the algorithm practically randomly pick where the connection should be.
Okay. Okay. Any more questions? No? Right? Yeah.
I have a question to your talk yesterday. I think that as we are studying the post-war urban structures, and we often observe that we have new buildings in surviving urban morphology in a way. So the post-war buildings do not really vary from the pre-war building, depending on the zoning and on the architectural design there. And yesterday you mentioned that you can find out a lot about the building age from morphology. So how do you how would you address this problem? Because I think it's, at least for the bombed cities, it's a quite usual thing.
Yeah, I think I may have used wrong term for this. It's not that we are necessarily able to predict the building age rather than the structure age, right? So if you demolish a building or it's demolished for some reasons and you rebuild it in a similar morphological pattern because the underlying, let's say, plot structure, underlying street structure is already there, we are able to predict how old the structure is, not necessarily how old the individual buildings are in the structure.
I agree. Yeah,
So
completely.
it's more a prediction of the age of the structure rather than the prediction of the age of individual buildings, even though the buildings are the features we are working with in the end. But it needs to be treated as more contextual type of prediction rather than per observation value.
I agree. And this also referred somehow to the Freiburg talk, because there you have this old town category, even though the old town was a reconstruction post World War. And just to mention this from the terminology, and I agree that also old town somehow is detached now from the actually age of the building. Yeah.
Yeah.
Like anything? No? Well, in that case, Martin, thank you so much for a second time. I will stop recording now. Okay. And then that's it. And